Hello everyone, my name is Tomas Valenzuela and I'm a biomedical engineering student in the Visible Heart Laboratories at the University of Minnesota. The abstract I'll be presenting today is using computational modeling derived from micro-CT scanning for the post-implant analyses of various cardiac devices. In 2016, it was found that over $170 billion were spent on medical devices in the US alone, and this number was projected to grow due to the advancement of transcatheter implanted devices. A lot of money continues to be invested in the R&D of these devices in order to make them smaller, to make delivery easier, improve their function or longevity, and to improve how they interact with the tissue they are implanted on. At the Visible Heart Laboratories, we reanimate swine hearts on a weekly basis and on occasion, human hearts. While the heart is reanimated, we are able to visualize implantation of various cardiac devices such as pacing leads and transcatheter aortic valves like the ones shown here. Above we have a pacing lead and below we have the transcatheter aortic valve. During this process, we're able to observe how the device is implanted, how it functions, and more importantly, how the heart functions after implantation. In order to perform further analyses of these devices, these hearts were formalin fixed after the devices were implanted in order for the heart to retain its end diastolic state. Once fixed, the formalin is rinsed off for 24 hours and then taken to a X5000 micro-CT scanner as shown in the figure above. We have found that micro-CT scanning to be beneficial over traditional CT and MRI imaging, achieving a high resolution with minimal artifact and no risk of device dislodgement. This is specifically in the case of MRI where hearts have been immobilized in an agar gel prior to scanning. Whereas in CT and MRI imaging, the specimen remains in place and the X-ray source and detectors are spun around it. In the case of micro-CT, the specimen is centered on a mount with the device in focus and the mount spins 360 degrees while the X-ray and the detector remain in place as demonstrated in the middle figure. Finally, specific parameters such as focal diameter, voltage, and current have been established based on the type and size of the device in order to achieve a successful scan. The images in the bottom are of two different coronary stents implanted in swine coronaries. If proper parameters are not chosen, you could end up with a scan like the one on the left where there is no distinction on where the vessel ends and where the lumen starts. You also have quite a little bit of artifact from the stent struts. If proper parameters are chosen, you can get an image like the one on the right, where we can distinguish between the stent, the vessel, and the lumen. In the end, we have recorded videos showing delivery, performance, and functionality of various cardiac devices. The majority of the micro-CT scanning work was initially focused on coronary stents, but we have recently started expanding these capabilities to other devices. For example, here we have a helix pacing lead that was fully implanted in the right ventricle of a swine heart. After micro-CT scanning with the device in place, we were able to measure just how much of the helix was embedded in the tissue. Here you can see that we had over 30,000 micrometers of the device implanted. We've also scanned cardiac valves, and here we have a TAVR, which was placed in a human heart. Through micro-CT scanning, we were able to check the final placement of the device, its apposition relative to the aortic root, and whether or not if it blocked any of the coronary osteas. Similarly, with coronary stents, we can see whether or not the stents were well apposed, and if not, how much distance of malapposition there is. Here we can see that we had about 842 microns of malapposition. In bifurcation techniques, where there is more than one stent used, we can measure exactly how much floating struts of one stent sticks out into the main vessel lumen. In addition to all these analyses and measurements that can be made, 3D models can also be generated from these scans, which can be further used for 3D printing, virtual reality, and performing computational implantations. All these combined can prove to be beneficial to physicians to gain a better insight on the devices they are implanting on a day-to-day basis and aiding medical device designers in designing the next generation of these devices. This concludes my presentation. Thank you for tuning in.